So we know that real gases don't exactly behave like ideal gases, and we also know that they behave most like ideal gases in low pressure, since there's more space between the particles at low pressures. And remember, in the kinetic molecular theory model, we said that the spaces between the particles are much greater than the actual particles themselves. So at low pressure, that assumption is more accurate. And also, real gases behave more like ideal gases at higher temperatures, since they're moving faster and the intermolecular forces between the particles are less effective, and we ignored those forces in the model. So this guy, van der Waals, made an equation to more accurately describe real gases, accounting for some of the differences in pressure and volume of a real gas. So first of all, the space available to a gas particle moving around in a container is less than the entire volume of the container. Since in the model we said that the gas particles have zero volume, but in real life they do take up space. So the space available to a single particle moving around the container is the volume of the container minus the space that the other particles take up. And so we can represent this new volume with V minus N times B, where N is the moles of the gas and B is some constant that you would have to find through experimental data. So we can rewrite the ideal gas law using this new expression for volume. And then next we need to correct the pressure. So since we ignored the intermolecular forces in the kinetic molecular theory model, the ideal pressure will be more than the actual pressure. And this is because since all these particles are pulling on each other and pulling each other into the group, then the particles will hit the container slower and less often. And remember, the particles hitting the container is what causes pressure. So the actual pressure that we observe in an experiment will be less than the expected pressure for an ideal gas. And the higher the concentration of gas particles, the more intermolecular forces there are, so the more we have to correct the expected pressure. And so the concentration is the moles divided by the volume, if we're talking about molarity. And so the correction factor is we take the expected pressure and subtract A, which is another constant that you'd have to obtain through experimental data, multiplied by the concentration N over V squared. And so this is the corrected pressure. And then so we can rewrite the ideal gas law again, accounting for this expected, or this pressure change. And then if we just rearrange this, we can get the van der Waals equation. So notice how it's the same form, PV equals nRT, but the pressure and volume have been corrected to more closely reflect the behavior of real gases.